2014 from UC Santa Barbara under the supervision of Joe Polchinski. And he's held postdoctoral appointments at the Stanford Institute for Theoretical Physics. And he currently holds a prestigious long-term membership at the Institute for Advanced Study in Princeton. Throughout his research career, Ahmed has been at the forefront of progress in the quantum mechanical theory of black holes. As a graduate student, Ahmed co-authored a highly influential paper about the potential fate of observers crossing black hole event horizons, which brought a fervor of renewed interest to the fundamental tension between the laws of quantum mechanics and general relativity. As a postdoc, he established a novel link between quantum gravity and the theory of quantum error correcting codes in quantum information, and this work has since led to a vibrant interplay between these subjects. Most recently, he has played a key role in dramatic progress understanding black hole evaporation due to Hawking radiation. And for these contributions, Ahmed was awarded the 2021 New Horizons Prize in Physics. Beyond his research accomplishments, Ahmed also has an impressive record in scientific leadership. Born and raised in Abu Dhabi in the United Arab Emirates, he is the first UAE national to become a theoretical physicist and has spearheaded efforts to establish theoretical physics in the region. It's our great pleasure here to have him today to tell us about new surprises in the gravitational path integral. Please join me in welcoming Ahmed.
Right, thanks a lot, Clay, for that very kind introduction. I should say that if you guys have any, if anyone has any questions during the talk, please interrupt me at any time to ask them. So let me begin. So for more than sort of 50 years or so, one of the primary goals in theoretical physics has been to reconcile quantum mechanics and gravity, and to somehow restore their sort of long lost love. The upshot of this talk will be that a sort of more careful analysis of gravity, when formulated using the gravitational path integral, removes a lot of this tension. And in some vague sense, gravity is nothing but quantum mechanics, but in disguise. There are many sources of the tension between gravity and quantum mechanics. The main one comes from studying entanglement and gravity. And so that's what I'm going to focus on today. So let's, sorry, is this thing moving? There you go. So let's first talk about entanglement. I should say first that I tried to sort of strike a balance between detail and just conceptual ideas. Please, again, if you have any questions, interrupt me at any time. Also, I'll try to be as provocative as I can. Okay, the first comment, or the first point, is that Einstein was wrong. Okay, he was wrong in a statement that he made about quantum entanglement, namely that it somehow implies some sort of non-local signaling, which he called spooky action at a distance. And of course, now we know better. We know this to be false, and we know that entanglement is simply sort of an sort of uncomfortably high level of correlation that you can have between two quantum systems, but no physical operation on one of them can ever affect the other. All that happens is that you have correlated results of measurements. Let's see this in a bit more detail. A quantum state between two parties or two systems, A and B, is a quantum state that does not factorize into a state on one multiplied by the state on the other. It's something that looks like the state over here. Can you guys see my pointer, by the way?
Yes.
Okay. So in this example, or in this quantum entangled quantum state, the state looks like 0, 0 plus 1, 1 plus 2, 2, all the way up to kk. And this is some vector or state in a product Hilbert space of the two systems A and B. And throughout my talk, I'm going to represent entangled particles as 2 points. These are the particles connected by some line representing the entanglement. What this line means is that you're supposed to sum over this index I. Now, the entire thing behind entanglement is that the probabilities for various measurements follow the following rules. So if you compute the probabilities using the Born rule, obviously if you check whether the state is in the actual state psi that you started with, you'll find that to be true with probability 1. But if you check whether it's if the two systems are in the state 0, 0 or 1, 1 or 2, 2 and so on, you'll find that it's true to probability 1 over k. But if you look at any off-diagonal measurement like 0, 1 or 0, 2, etc., you'll find that to be 0. Okay? That's the entire thing behind quantum entanglement. This point about there not being signaling from A to B is simply that operators or operations that you do on A and B commute. Something interesting about entangled states is how their subsystems behave. So if, in particular, you find that subsystems behave randomly. Suppose you're interested in the state of a subsystem of the subsystem B. You can compute its state as a density matrix by tracing out the system A. That's this operation here, which involves diagrammatically starting with the state and the ket and the bra vector and tracing out 1/2 of the system. The result that you get is this expression for the density matrix. It's proportional to the identity operator. What this means is that the measurements, or rather the probabilities for getting any result on B is simply uniform, and it's 1 over k. The point is that this state is not a superposition of the various measurement results. It's what is called a classical mixture. And so this state is often called, such a density matrix is called mixed. The point that I'm trying to drive, or sort of drive home, is that with entanglement, there always comes some randomness. And by randomness here, I sort of mean the usual kind of randomness that everyone is familiar with, namely that if there's a possible sequence of results that you might get, no measurement result comes with probability equal to 1. Mathematically, that's isomorphic to the statement that the sum of the squares of the probabilities is less than the sum of the probabilities, which is equal to 1. One way to compute or to diagnose entanglement is via something called the swap test. The point here is, so the way you do this is you start by doubling the system and ask, what's the probability that the doubled system remains the same after interchanging the 2 copies of B? Okay, that's computed by taking the 1 copy of a doubled system swapped and computing its overlap with the unswapped double copy of the system. This can be written as sort of an expectation value of some swap operator. But that's not too important. The important thing here is that this expression can be written as a function purely of the density matrix of the system B. Okay, so the density matrix of the system B contains in it information that whether or not it is entangled. If you compute trace rho B squared, it's given by a diagram like this. The rule for these diagrams is that every closed loop gives you a factor of k, and the 1 over k squared outside here is simply a normalization that came from the normalization of the state that we started with. Now, clearly 1 over k is less than 1 for k larger than 1. And so this quantity trace rho squared computes simply the sum of the probabilities squared, and it's equal to 1 over k, and it's less than 1, and therefore you've confirmed that you have randomness. Okay, I introduced this method for computing entanglement because it will be relevant later when we talk about when we compute entropies in gravity using the path integral. So that's everything I wanted to say about entanglement. Now I'm going to switch gears and talk about the path integral. Okay, so the path integral formulation of quantum mechanics, in my opinion, is the most elegant formulation of the theory. And it goes something like this. So you say, suppose I have a particle that starts at some location xi at some point in the past. The quantum state of the particle in the future can be written like this. It's a superposition of possible final positions weighted by some wave function. The wave function of this particle is what this formulation says is that the wave function is equal to the integral of it's integral over all possible paths that the particle can traverse, going from the initial xi to the final xf, weighted by the exponential of the action of the particle. Okay. All right. Sometimes these path integrals are hard to compute. And sometimes it might be interesting to see how the classical limit, how classical trajectories or classical physics emerges from quantum mechanics or from the path integral. And you can do this by taking the h bar goes to 0 limit. So you are removing quantum mechanics. And what happens when you do this is that the exponent in the integral becomes extremely large. What this does is usually it justifies a sort of saddle point approximation or stationary point approximation where the integral is highly peaked at the locations where or for paths that satisfy the equations of motion from the action S. Okay, so rather just the saddle points. So what happens to your integral is that it breaks up into a sum over these contributions, sometimes called saddles. About every given saddle, there could be some small fluctuations. So in the classical limit, we have a ball that just rolls down a hill. That's how it works in classical mechanics. But there could be some small fluctuations which are sort of just invisible to everyday, to our experience. And here I give sort of two examples. Here you can have here. Have something like a cylinder, for example. What can happen is the particle can either just stay where it is, or it can go around the cylinder. By the way, I got a warning that my connection is unstable. Am I still with you guys?
You're still with us. You broke up for 1 second. Maybe explain the plane again.
Okay, the pictures here. Here I'm just showing a particle, or rather a sort of possible classical trajectory for a particle. Here, time goes upwards on this sort of sheet, and this describes a particle that just stays sort of in place. But if you have a particle that lives, like if the universe is a cylinder, then you can have various possible classical trajectories. You can have a particle that just stays where it is, or it could possibly go around the cylinder. Here, I'm just trying to give examples of possible classical trajectories that would emerge from such a path integral. Okay, that's my lightning review of the path integral in regular quantum mechanics. Next is the gravitational path integral. the rules sort of behind how to formulate this come primarily from Hawking and also many, many, many works that I couldn't list here. The idea is that while for a particle, the paths are the various trajectories on some given spacetime, in gravity, the paths are the different spacetimes, okay? Usually subject to some boundary conditions. So if you want, so here, the wave function of some given configuration of spacetime at some future, at some given time, the path integral says that to the past, it could have been anything. Okay? And I should say that for the most part, this formulation of gravity is just a complete mystery. And really the only regime in which we have handle on it is in a classical limit, is similar to what I described a few moments ago. I'll discuss that a bit more in a sec. The simplest kinds of gravitational theories to consider are those that have some sort of boundary on which you can anchor things. So here at the bottom, I say I'm going to integrate over all possible spacetimes that emerge from some given boundary in the past. Okay? So here I give some example spacetimes. So it could be just a closed circular universe that emerges out of this circular boundary, or it could branch into 2 universes, or 3 or 4, or and so on, and it could have complicated topology, etc., etc. Okay. But so that's gravity by itself. But we're interested in a theory of the universe where you have both gravity and matter and us. And so you need a sort of everything path integral, where all possible paths of everything are integrated over. In particular, you're integrating over all possible spacetimes and then over all possible paths of particles propagating on the spacetime. Again, such a path integral will be weighted by the full action of the theory involving action for matter on some given spacetime, and also maybe just the action of gravity by itself. And something that I want to, well, considering a theory where you have gravity everywhere is kind of complicated. A simpler model to study is what I'm defining here is as a hybrid model. So here I have a universe where, or a theory where for most locations in this universe, gravity is turned off. So the path of gravity in those regions does nothing. So the spacetime is fixed, it's flat. But then I imagine that in some region here, gravity can fluctuate. Okay? And the idea is that what this path integral, the kinds of universes or states that it creates for me, let's say at some future time, let's say t equals 0, is that of a disconnected spacetime where the gravitational region is able to branch off into a baby universe. Okay? The original fixed spacetime part of this universe, I'm going to call the parent universe. So this kind of hybrid model, one has a parent universe and a baby universe. Now, this model seems very weird. Why should I be interested in this? Well, I said first, it makes things simple. Second is that it's a good model for an evaporating black hole. Okay? The claim is that when a black hole evaporates, in some sense, it branches off into a baby universe. Here, on the left, I have the various stages of black hole evaporation. In this picture here, I have a collapsing star. Once it collapses sufficiently, once it passes through its Schwarzschild radius, it develops a horizon. That's the dashed line here. That's the point of no return. Something that we learned from Stephen Hawking is that once you have this horizon, there's this process that takes place, often called a pair production process, whereabout this horizon shrinks, or rather this black hole starts to shrink. What happens is that two particles, it's often described as two particles pop out of the vacuum. One of them goes away to infinity, and the other one is on the inside of the black hole, and therefore it simply falls and crashes into the singularity. So again, the black hole shrinks as you create more and more of these particles. And the structure of the spacetime really looks something like this. Like the inside, even though the horizon shrinks, the volume of the inside actually grows. And so it looks like it's slowly detaching off as a function of time as the black hole is evaporating. And once it evaporates away completely, you're simply left with Hawking radiation in the universe and entangled with particles that are in this closed universe somewhere else. The picture looks like the picture on the right. So you had a star that collapsed into the black hole, and the only thing that remains in our universe is this Hawking radiation. And they're entangled with particles inside the baby universe. This is sort of the source of the information paradox. It's the point that you could have, this black hole could have been started, or rather the star that formed the black hole could have been started in some pure state psi, but the final state, at least from the outside perspective, is just a Hawking radiation, which is in a mixed state, the density matrix rho. And so from the outside perspective, it looks like the sort of black hole formation and evaporation process transforms a pure state into a mixed state. Recall that when you have a mixed state, you have randomness. There's no measurement that comes with probability 1. But for the pure state, there isn't randomness. You can just check that the state is in the state psi, and you get that to be that measurement succeeds with probability 1. And this non-conservation of the probability going from psi to rho is the information paradox. Okay? And the point here is that we want to analyze this question, revisit this question, using ideas from the gravitational path integral. And so if we go back to our model and we work in the classical limit, h bar g Newton goes to 0, the leading saddle looks a lot like the black hole spacetime that I just drew. Okay? And I'm going to imagine that in this model, I have entangled particles, one that stays outside in the parent universe, and it's entangled with its partner inside the closed universe. Okay? So in the semi-classical limit, the quantum state looks like an entangled state. It's psi bp, b stands for baby, and p stands for parent. It's an entangled state like that we discussed at the very beginning when we discussed entanglement. And because we want to study, this is a model for a black hole, K, then the amount of entanglement is the exponential of what is called the Bekenstein-Hawking entropy of the black hole. It's a very, very large number given by at least the exponent is given by the area of the black hole in Planck units, the black hole when it was initially formed. And so in this model, the particles in the parent universe seem to be in a mixed state. Okay, so reconfirming the information paradox. We can also check that this result is, well, we can check this mixed state of the parent universe by computing a swap test. So how do we compute the swap test in this case? So semi-classically, if I want to compute the density matrix of the parent universe, so remember the swap tests, it involves computing just trace rho squared of the system you're interested in. So the first statement, the first step is to compute the density matrix, rho of p. You get that by simply tracing out the baby universe. And the picture you get is something like this for the density matrix. Okay? Now, if you now to compute trace rho squared, well, you need to multiply rho times rho. So there's some matrix multiplication involved. That's the swapping that's shown here, okay? And there's a 1 over k squared that comes from the normalization. And now from this picture, we can simply evaluate it by computing the number of loops that we have. Now looking at this picture, and you can sort of trace it. So you go this way, you go through this wormhole, out this way, around that wormhole. You find that there's a single loop. So a single loop, that means it's a factor of k. K multiplied by 1 over k squared is just 1 over k, which is less than 1. And indeed, we've confirmed that in the semi-classical limit or semi-classical state, P is mixed. Okay, so this is the information paradox. Rather, this is a simple diagnostic of the information paradox. Often you need to compute the actual something called the von Neumann entropy, but this is a quick, it's a sort of a quick and dirty method to check the same thing. But we made a mistake. So let's do the swap test again, but do it a bit more carefully. In particular, something you can do is you can sort of delay the application of the semi-classical limit. In particular, you should allow for gravity to make other possible connections. In particular, in this picture here, another possible connection is the one that connects this wormhole to the wormhole on the, or rather this baby universe to the baby universe on the other side, okay? So here the words are, it's a wormhole that connected the two different baby universes. And if you consider such a possible connection, okay, then you find that this complicated diagram can be sort of unwound, and it looks like it's just a square of the trace of rho, which is just equal to 1. Okay, so that's a very simple trick, and the result is very, very simple. So let me just contrast the two pictures. The picture on the right is sort of the naive answer of what you'd expect for how to connect the baby universes, assuming that you work in the semi-classical state, in the semi-classical limit. But if you allow yourself to apply the semi-classical limit a bit later, you'll find that there are other possible connections. Okay, so this can go all the way around. And therefore, when you compute the trace of rho squared, so let me backtrack. These two different possible connections, they correspond to two different semi-classical spacetimes in your path undergo, and or rather two different saddle points of the path undergo, and therefore you're supposed to sum over them. One of them, the wormhole saddle gave us 1, but the naive saddle gave us 1 over k. Okay, that's a saddle that often, well, we've been calling it the Hawking saddle. And for the black hole, in the black hole case, 1 over k is simply e to the minus s Bekenstein-Hawking, and this is approximately equal to 1. So it looks like when you include non-perturbative effects, even though these are in some sense classical events, or sort of classical events, nevertheless they change the answer dramatically. Okay, so non-perturbatively, you find that the parent universe is almost pure. So the trace of rho squared is equal to 1. And something that was important to get this answer is that there was a large amount of entanglement, right? It was important that k is large. If k was not large, we would not, this answer would not be close to 1. You'd get a nonsensical result. And
Can you clarify something, Ahmed? The wormhole saddle being larger than the naive saddle makes it sound like the expansion is bad. Because usually you would think that the other saddles are small corrections.
Yes, in this particular
Help me think about that, get some intuition.
well, in this particular calculation, or this example, I claim that one of the saddles is very large, it gives you 1, but all the other saddles are tiny. And so the correct approximation to your integral is just the first saddle that's equal to 1. So the other saddles are non-perturbatively small corrections. Did that answer your question?
I see. So it's the naive classical saddle that is supposed to be viewed as a correction to the dominant answer and is in fact negligible. I see.
Exactly.
Thank you.
Yes. So, but let me emphasize that situation is only for this model. Let me explain. I think I explained this on the next slide.
Oh, wait, sorry, I have a quick question.
Yes, go ahead.
Doesn't trace of rho squared always have to be less than 1? Isn't it kind of weird it's a little bit bigger than 1?
Good. So first, I didn't tell you about the signs. Second, well, I wasn't too careful about the signs. Second, there's actually a normalization issue. There's a more careful calculation that you can do, which gives you 1 exactly. But I just for the sake of keep things as simple as possible, I ignored that. But you raised a good point. It's actually non-trivial to see how to restore sort of exact unitarity, if you will. Okay, the punchline here is that this would predict that the final state of the Hawking radiation is pure. This same effect, this competition of saddles, is what is sort of the main punchline of these recent results that led to the so-called island formula and the page curve for the Hawking radiation. So here I have a picture of a spacetime where of a black hole, of an evaporating black hole spacetime, and the question here is, how does the entropy of the radiation evolve as a function of time? Okay? And the punchline, well, the result that you get from Hawking's original calculation of assuming the so-called Hawking saddle is an entropy which continues to grow for all time until the black hole evaporates away completely. It's simply the statement, again, that we keep having more and more of these entangled particles across the horizon. But there's another saddle that comes in at some point, which is the analog of the wormhole saddle that I discussed here, where when you compute the entropy of the radiation, it involves the entropy of the union of the radiation region and some region inside the black hole called the island. And even though I didn't discuss the von Neumann entropy too carefully, the fact that you're including, well, the fact that you're including both the radiation and the island in the entropy computation, you don't count the entanglement between them. They are part of the same system. So you have two entangled particles, they're entangled with each other, but this pair is not entangled with something else. That's the point here. Anyways, in this process, this is more, in this process, or in this example rather, when you compute the path integral, or rather when you compute the von Neumann entropy using the path integral, you find that there's a competition between two different saddle points. They're both extremely tiny, but there's a competition between them. And when these saddle points are weighted by e to the minus the entropy, and therefore the answer that you get for the radiation ultimately is going to be the minimum of the entropies. Essentially, when the Hawking saddle answer is larger, when the von Neumann entropy is larger than the wormhole saddle, this means that it is suppressed more, right? The saddle is e to the minus s. Okay, that's one way to think of it. Anyways, so this minimum between the two different saddles gives you the famous page curve for the evolution of the entanglement entropy. Okay, that's all. Okay, this is everything I wanted to say about computing entropy. The next thing I wanted to say is, or talk about, is holography. So there's this extremely interesting and useful idea due to Juan Maldacena that a theory of gravity can be equal to a normal quantum system. So this idea goes by the name of ADS-CFT. What this says is that a kind of gravitational theory in a kind of space-time called anti-de Sitter space is equivalent to a quantum field theory that lives on its boundary. It's a kind of quantum field theory with very interesting symmetry. And the picture that the picture of this setup is that it's sort of this can of soup. You have the cylinder, the bulk of the cylinder or the bulk of the can is the ADS space, where you have gravity and strings and so on. And the boundary of this can is where you have the conformal field theory for just a regular quantum system with no gravity. And these two are supposed to be equivalent to one another. The claim here is that in the same sense, the baby universe in the model that we discussed can be thought of as a subsystem, or that it's encoded in the parent quantum theory. Okay. The only difference between this picture and this picture is that in the baby universe example, it's not equivalent to the parent quantum theory, it's just a subsystem of it, or it's encoded in it. And the punchline is that what's going to achieve this is, again, just a gravitational path integral. And this gives an explanation for why ADS-CFT works. It works because of the gravitational path integral. And I'll give sort of a very quick way to see how this works. We want to demonstrate holography. Okay. In particular, the idea is that you want to find an operator on the parent universe which is able to change the state of the baby universe. Okay. So here I have so here's some state of the parent union, the baby universe, and the blue particles just represent some entanglement. But suppose we have another particle, the red particle, in some state I, okay, which falls into the baby universe. I claim that the following operator, defined abstractly in this way, can change the state of this particle from I to a j. Okay? Here I'm defining the operator by defining its bra and its ket. Okay? What I'm going to do now is simply act to this operator all on the state psi. What happens is that the bra of the operator joins the parent universe in this way. And because of the entanglement, because of this connected blue particle, the gravitational path integral finds it most convenient to connect the wormhole or the baby universe in this way. But when you have something like this, this is simply trace of rho, which is just equal to 1. The remaining, the thing that remains is simply the ket of the operator that you started with. The ket is right here, but the ket of the operator had the red particle in the state j. Okay? And so you simply get the state psi back, but the state of the particle has been changed from I to j. The point is that the way that the operator changes the state of the baby universe is by sort of weaving a wormhole into it and replacing the baby universe with a new baby universe with a different state of the particles inside it. Okay? This shows that the baby universe is in some sense encoded in the parent. The last thing I wanted to talk about might have gone over, I guess. Did I?
You're fine.
Fine. Okay. The last thing I wanted to talk about was just this connection of gravity and quantum error correction. Now, what is quantum error correction? This is a feature which is needed to build fault-tolerant quantum computers. The problem with building a quantum computer is that the state of the qubits in your quantum computer can possibly decohere because of interactions with the environment. And one way to sort of combat this is to store your information in a smart way so that these errors or so that the environment doesn't affect the information encoded. One way to do this is to store the information non-locally in your collection of qubits. So you can have like 50 qubits and you can encode, say, suppose, so you encode things redundantly, you encode 1 qubit's worth of information in 50 qubits, for example. The idea is that, so you make the assumption that the environment can introduce errors, but it only introduces them in a local way. Okay? So here I have sort of a register of qubits, for example. You take the state psi of some information you're interested in encoding. You encode it in some non-local fashion in all of your qubits. Now, if there's an error that happens to one of your qubits and you lose one of these qubits, it's fine, it's okay, because you can decode the same state from the complement of the corrupted qubit. Okay? Such a quantum code is often called an erasure code. And the claim is that gravity can do this. The first demonstration of this was done in the context of ADS-CFT. So the way that the bulk ADS theory is encoded on the CFT boundary follows so the patterns of quantum error correction. So the observation that we made is something like this. If you look at a spatial slice of your ADS space, that's what I've represented here. So the spatial slice, along with the state of some particle in the center, psi, is encoded on the boundary slice, which I've partitioned into 3 systems, A, B, and C. The question is, which collection of the boundary systems do you need in order to recover the state psi in the center of the spacetime? The claim, at least in this very simple setup, is that the state psi in the middle can be reconstructed from any from any 2 regions. So, for example, B and C, and so any single region, for example, A, can be corrupted or erased. You can simply ignore it. Okay, so we observed that that the way holography works, well, it has this feature, and so it looks like it's quantum error correction. And there are various other checks. This is just the simplest way to see it. And the claim here is that it's the path variable again, which guarantees this feature. This topic is a bit complicated, so I'm going to be extremely hand wavy, more than I've been so far. So the idea here is, suppose you have a closed universe with a bunch of particles that are entangled with some external systems. So here I have the blue particle inside the closed universe, which is entangled with some particle A, and B, the red particle inside is entangled with B, and the green particle is entangled with C. And then you imagine you have some 4th particle in the closed universe in the state psi. Here, this brown particle. And then the question is, which collection of A, B, and C can affect or can change the state of psi? And it's essentially the same calculation we've been doing. You find that there's a competition of saddles or a competition of wormholes. It's from the gravity particle perspective, it's more likely for a wormhole connected from BC to join into your closed universe than it is to go from A, essentially because there's more entanglement between BC and the closed universe. Okay, so gravity again gives us this result. that's pretty much everything I have to say. So let me wrap up. So I discussed some interesting interplay between entanglement and gravity. I showed how I give a model in where entanglement induces the creation of wormholes and directs them where they need to go to give us sensible answers. These wormholes lead to sort of non-local effects. Again, so remember Einstein from the very beginning, it turned out that he was right. So entanglement can lead to non-local effects, but not in the sense that he was worried about. Moreover, these wormholes led to a vanishing entropy for the evaporating black hole, and it gave us, or it implements quantum error correction. So maybe Google is trying to hire quantum gravity now. Okay, that's everything I had to say. Now I need to go work on my taxes because gravity won't do it for me. Thanks.
Okay, thank you, Ahmed. Let's take some questions. Please raise your hand if you have questions. Okay, perhaps I can start while people are thinking. So, I mean, how important is it in this story that the wormholes are actually saddles? I mean, you're not really solving equations of motion in, you know, four-dimensional gravity plus matter.
One minute. Well, I mean, in the cases that were studied, well, sorry. I mean, this entire thing is about solving the equations of motion. Is your question about 4 dimensions or just the philosophy of including saddles versus not saddles?
Well, no, I think I understand that in a semi-classical expansion, it's dominated by saddles. I guess it's more of a question of if you are outside the regime of low dimensional gravity, are there actually these saddles? To what extent do we know that there are these saddles? Or is it more like a cartoon that we hope that there are these saddles?
Well, I mean, there are examples in also in higher dimensions where you can have wormholes. But if your question is about sort of let me take a step back. There are examples for higher dimensions or in higher dimensions where these wormholes and saddles, this entire story runs through. But these are kind of special examples which involve holography, which involves higher dimensional versions of ADS-CFT. And you can indeed find these saddle points and they give you the right answer. But the hope is that you can consider a more natural theory and that this focusing on just the saddle points would also give us the same answers. I guess maybe that's the answer to your question, that it's simply a hope for more realistic theories, but we don't, I mean, there's no sharp argument to say that we shouldn't expect them there. It's just harder to find.
Sure. Okay. Thank you. Noah?
Yes, hi. I had a question about what this has to say for like the original Hawking argument that information is lost, in the sense that if we are computing, you know, entropy with the path integral and we're summing over classical saddles, that's not like, how does that explain like what was wrong with Hawking's original calculation? Like if he was computing a state of just matter in a classical background metric, when we do this, you know, gravitational path integral, does it give any explanation of what's going on with the the quantum state of the space-time itself, is that anything we can like read into or like see where the space-time state, you know, doesn't seem classical?
Very good question. So I don't have any comments to make about the state of the space-time metric, but I do have a comment to make about the state of the matter. So yeah, so in Hawking's original calculation, he was working again in this semi-classical limit where he just focused on, well, he focused on one saddle, and he studied the state of the radiation propagating on this background. And then he looked at that state, and then he was able to deduce what the von Neumann entropy is going to be of the radiation. The claim here is that that argument is too quick. And in order to compute the von Neumann entropy, there's a more careful way of doing it, which involves considering many copies of the system. And then it's just by well, when you consider many copies of the system, like for example, trace rho squared that I considered, you get these wormholes. Okay? The point is that if you consider the more careful calculation of the entropy, which involves duplicating the system, restricting to the space-time that Hawking considered is a bad approximation, because you can have these wormholes. The wormholes, you find that in certain regimes where essentially where the paradox kicks in, those contributions are more heavily weighted in the path integral than the configuration that Hawking considered. Does that answer the question?
Yeah, thank you. But so you would say that that we can't really use these wormhole saddles to really make any claims about what exactly was wrong with Hawking's original calculation. That's still sort of a black box. Like, if this doesn't answer questions about that.
Whether or not this is a black box, I mean, I would say yes, these calculations are kind of a black box, but why isn't, I would say Hawking's, well, because it depends. This might be a matter of interpretation. I think I would just say that in these calculations, you can identify various terms, and you can identify which term is the one that Hawking focused on, and the rest of the terms were ignored. So I would say at that level we can sort of pinpoint Hawking's mistake, if you will.
Okay, thank you.
Great. Okay, Carlos. That was your question? Okay. Dane.
Yeah, hi. So what is the justification for the claim that the calculation with the copies is somehow more correct or more careful than the calculation with just one copy?
Well, the only way that I know how to compute entropy, von Neumann entropy, involves taking trace of rho to some power. That really is the starting point. Okay? So, and then trace, well, let me give you that as an answer and see if there's a follow-up. So by definition, the way, well, the most convenient way or the most careful way of computing the entropy is by something called the replica trick, where you first duplicate the system, evaluate the result, and then sort of do something which is, well, then take a certain limit of the calculation. Do you have a follow-up on that?
That's good for now. I'll have to think about it some more. Thanks.
Okay, Nathaniel.
Hi. I think like Juan Maldacena gave a talk earlier this year talking about resolving the information paradox with for black holes with a semi-classical approximation, and then something involving that you have the entangled particles being emitted, and then if you had fed it somehow into a fancy quantum computer with the correct algorithms and stuff, you'd be able to recover the information that fell into the black hole. So I was wondering how a scheme like that would work, or links into what was talked about today with having the other paths between the wormholes to resolve the information paradox.
Yeah, so essentially this talk was aimed at giving the details of Juan's talk. So all the effects that Juan talked about, I think it was last year or something, are generated because of the wormholes that I discussed. So it's really the same paradigm, if you will.
Cool, thanks.
I'd like to ask another question. So maybe a more speculative question. Do you think that wormholes or maybe other semi-classical solutions are relevant for other kinds of singularities? Like, do you think you can say something about cosmology by studying semi-classical gravity?
That's the $1,000,000 question. I mean, it gave us so much here, but
it's almost shocking it gave you so much. I mean, there's nothing that really prevented Hawking from doing this calculation.
Yeah, I just think that I really it's really a mystery. Well, it's kind of, I mean, Hawking's the one who taught us how to sort of work with the gravitational path and go. I think the only issue there is that I don't think well, you asked me why didn't he stumble on this resolution or this way of doing things, is the replicate trick wasn't around. I think it might have been around during this time, but just wasn't as famous or familiar to everyone.
Seth, go for it.
Thanks, Ahmed. That was fantastic. Could you say a bit about, in your opinion, what we're learning about observers closer to their horizon?
Excellent question. So there's
Is the question, is there a firewall?
Yeah.
More generally. Oh, well, I mean, that's a good one to start. Sure, certainly.
Yeah. So I made this. So I made this point about holography here, that the baby universe is secretly part of the parent universe. In this picture, that translates to the island being the interior of the black hole being secretly part or encoded in the radiation. That sort of statement already resolves the original, or rather the very first firewall argument. There was this argument for monogamy, and a Hawking particle had to be entangled with something inside the black hole, but also had to be entangled with something far away from the black hole. But now what we're learning is that the inside of the black hole is equal to the thing far away. So there is no violation of monogamy of entanglement. So that would seem to suggest that the black hole horizon is maybe smooth and there's no firewall. I think that's my position currently for at least these kinds of black holes. These black holes that are sort of formed from collapse, or well, these are black holes that are sometimes called atypical black holes. So that you can consider a black hole which is sort of drawn at random from the Haar ensemble or the thermal ensemble, etc. Those I make no statement about. But for these simple black holes, I would say that if you excuse the pun, the firewall has evaporated away.
Gotcha. Cool. Thanks.
Carlos.
Yeah, could you explain this minimum relation, please, in an intuitive way?
Do you mean how to apply it, or do you mean where it comes from?
Yeah, where it comes from, yes.
Okay, so the computation for the entropy involves, again, evaluating some path integral. The path integral is, well, this path integral, we decompose it as a sum over saddles. Each contribution from every saddle, say the Hawking saddle or the wormhole saddle, it turns out, I did not explain these details in the talk. It turns out that they are weighted by the exponential of minus the entropy computed in that saddle. So it's going to be, roughly speaking, the exponential of S, well, yeah, the exponential of the actual entropy is equal to, sorry, the exponential of minus the actual entropy is equal to the exponential of minus S von Neumann rad plus the exponential of minus this quantity here. So now there's a competition between these two terms. When S von Neumann is smaller than the wormhole saddle, when the Hawking answer is smaller than the wormhole answer, the Hawking answer wins. You can take the log of both sides, so the entropy is just equal to S von Neumann as computed by Hawking. But then at some point in this time evolution, after this point in the middle, often called the page time, the two different saddles exchange dominance.
Mm-hmm.
Then it's this one that wins over this one.
Are you, technically, are you working on a Euclidean time, or how do you define the path integral? I used to know that there were some problems with the definition of the path integral, that you talk like it was a simple calculation, but
There are too many problems with the path integral. I completely agree with that, and it's not clear that a priori that we're doing a well-defined calculation here. The punchline of these recent works is that if you ignore all of these problems and you just focus on the saddle points, then you get these results.
okay.
And just as a final comment, the most careful calculations, as you said, they do involve working in Euclidean space. But I didn't want to talk about that today.
Okay, very good, thank you.
Mhm.
Nima.
So I have a question about this last comment. So most of this results comes from doing Euclidean path integrals, and then you discover other saddles. Have you got any sense of, so should I expect that if I was to do this computation in real time, there is lots of little interactions that sum up to give the saddle? Do you expect that you learn some non-local small physical thing that's happening over time for the information to come out, and whether you have any clues as to what that mechanism might be? Or do I really need to work through string theory and figure out the details of the UV to figure out what's happening?
Honestly, my bet is that these methods will not tell you anything about the quantum state. But essentially your question is, what are the details of the quantum state as a function of time? And
Well, is it true that in principle, if you had all the rho to the n, you could in principle reconstruct the full density matrix? Yeah. And
yeah.
so is there some n at which you expect this computation to break down, and then you need to include the details of the UV? I guess in principle that would tell you how much of the quantum rho that the full density matrix you can construct.
Let me see. So, it's not clear to me that these calculations break down at any n.
But they must, right? Because otherwise you can reconstruct the full density matrix, then you know everything that's happening in principle.
Well,
I guess that's another way of asking my question. Can you reconstruct the full density matrix as a function of time?
yeah, that's an interesting question. Yeah, I guess if you do go to high enough n, where n here would have to be something like, I see.
It should be like e to the s. Or...
Yeah, it should be e to the s. Then yeah, I guess what might happen is that at some large enough n, there just won't be a trustworthy semi-classical approximation. If that's effectively what's going to happen.
Do you know what are the scales that are competing here?
I'm not sure.
No.
I'm not sure what's relevant for this question.
Okay. Thanks.
Any other questions? Emil, go for it.
Sorry, I was muted. Yeah, maybe a follow-up to that last series of questions. So if I ask about what the state of the radiation is, so I could imagine, if I'm powerful enough, I can watch this black hole evaporate. It's coupled to some bath of free photons. And the claim is being made that the island is part of the photon bath. And so at the end of the day, the black hole is evaporated. I can now decouple the system that contains the black hole from the photon bath. And I can just look at the photon bath and say, what is the list of photons and the properties of their quantum entanglement? And so I have the Hawking photons that I've been watching come out of the black hole systematically. And then there's some other part of this photon bath that somehow mystically contains these correlations with the interior of the black hole with the Hawking photons. So where in my photon bath is that extra piece? It seems like the claim is being made it's part of the photon bath, but it's in some very complicated entangled state. But it's a photon bath. I can just look at the photons in it and ask what their correlations are. So where are these extra photons that are unitarizing the Hawking photons in my photon bath? Are they being systematically emitted at some rate as the black hole is evaporating so that they become part of the bath? But then I would want to know, it sounds like some very non-local process. You're saying that somehow magically new photons are appearing without any apparent causation from any process that's going on nearby the black hole.
So the new photons that are appearing, do you just mean the Hawking radiation?
No, I mean the things that are making the Hawking, that are unitarizing, or that are purifying, the Hawking photons. At the end of the day, I have just some photons, and I just have some photon bath. It's in a pure state because the black hole completely evaporated, and so the Hawking photons are not pure by themselves. But so there's something else in the photon bath that's purifying the Hawking photons. And is there any idea, say, what their energies are? Are they some very diffuse bath of infrared things, or are they just other normal photons of energies comparable to the Hawking photons? That seems unlikely, because I would have seen them coming out. So is this some analog of like the soft radiation that people have been talking about, or something else?
I'm not sure about the last comment, but the point here is that given these results, the conjecture is that encoded in the state of the photon bath, in the details of the state of the photon bath, is the information about what's inside the black hole. Okay. I feel like your question might be about how to compute these details. Is that did I miss the mark completely?
Well, I guess what's confusing me is how would I encode this in a photon battle? You're doing something which I've accounted for all the energy of the system, right? In the Hawking photons that I've watched come out.
Yes.
Okay. So it sounds like you're saying there's something about this photon bath that costs zero energy and yet somehow purifies the Hawking radiation.
No, that's not what I'm saying. I don't think I'm saying that. You just have, say, n photons in your bath, and they're in a pure state. I'm not saying, so if you look at these n photons in the semi-classical, in the wrong calculation, those n photons would look like that they're in a mixed state. And if I'm understanding the confusion is that maybe that the picture is that somehow I have n photons in a mixed state, but they're entangled with something that's not visible. And that's
Called the island.
No. That's in the semi-classical limit, that's what it looks like. But the conjecture is that the exact quantum state of the n photons just by themselves in the bath is a pure state. It's not that they're mixed and they're entangled with something imaginary or, as you describe, some diffuse thing in the bath. And there are various pictures that you can try to describe the system in. You can either use what we've been calling sometimes the gravitational picture or the semi-classical picture. In that description, one would say that you have n photons in the bath that, again, in this picture, n photons in the bath that are mixed, but they're entangled with the inside of the black hole. Okay, that's one picture. But now the claim is that there should be another picture where you ignore the interior of the black hole altogether. And in a more exact theory, the n photons in the bath just by themselves are pure. I don't have such a theory, but that's the most, well, what we find the most sensible way to interpret these results.
Okay, so then it sounds like you're saying that something is reaching from deep in the interior of the black hole and adjusting the phases of the photons you already have by some very non-local mechanism.
Well, I would say that as the
in order to purify the state.
Well, I would say slightly differently. I would say as the black hole was evaporating ever since it was created, there are small corrections to the states of the Hawking quanta coming out of the black hole. And if you work in an exact theory, string theory or whatever, you'd be able to calculate these corrections. And you'd find that the radiation that the photons that are accumulating in your bath, that if you compute their entropy, it follows the page curve. If you compute the normal entropy, just negative trace rho log rho of simply the photons in the bath, in an exact theory, that should follow the page curve. We're not contradicting that.
All right, I'll have to think about that.
Thanks,
All right, thanks.
Okay, it doesn't look like there are any more questions. So let's thank Ahmed for a wonderful colloquium and for all these questions. And yeah, great.
Thanks a lot. This was a lot of fun.